Number 64. Nicotine, which is C10H14N2, is a base that will accept 2 protons. And then they give us the 2 ionization constants. So we have Kb1 is 7 times 10 to the negative 7th, and Kb2 is 1.4 times 10 to the negative 11th. What is the concentration of all species present in a 0.05 molarity solution of nicotine? Okay, so they want the whole shebang here, right? What's the concentration of each species present? When they're talking about that, what they basically want you to find out is they want you to find what's basically all the species that are present, but specifically at equilibrium. Now, the only thing that they gave us was that they told us that we're preparing this in a 0.050 molarity solution of the original nicotine. So what they gave us basically was the initial concentration, right? This was assuming that the base did not accept any protons. This is just saying that at initially, we had a 0.050 molarity solution. So when they're asking for when they're giving you initial concentrations, they're asking for things at equilibrium, and they're giving you a base. They said that it was a base, and this is not one of your 6 bases. This is a weak base. So with all of these together, they gave you initial concentration, they're looking for equilibrium things, and they gave you a weak base. We got to do an ice table. Yay. So let's start it off. We're dealing with the base, so we're going to do C10, and maybe I'll just put it over here. C10H14N2. They're saying it's a base, so I have to add water. With bases, you always have to add water to your balanced equation, or else the equation is not going to be balanced correctly. This is a weak base, so it's at equilibrium. And remember, bases will accept a proton, but it could only accept 1 at a time. So in this case, I'm only going to bring 1 hydrogen from the water to the nicotine. So in this case, it would be C10H14N2, and then H. When you gain a hydrogen, you always become a positive charge, or 1 plus what you had. This was 0. Plus 1 is a plus 1. And then this was the acid. Remember, acids lose hydrogens, so you'll drop the 2, go to a 1, and that's always OH minus. And if you do produce OH minus in solution, you know that you're going to be a base. And since I only picked up the first hydrogen, that is the Kb1. The 1 stands for the first hydrogen that was picked up. So in this case, I only care about Kb1, which is 7 times 10 to the negative 7th. Okay. Now, let's do that ice table. So maybe what I'm going to do is I'm just going to put that down, put this down, right? We're dealing with bases, so I'll do everything in blue, ICE, right? And we just want our states. Anytime that you see charges, that's always aqueous. So these will be included in my Kb equation. Weak acids or weak bases are always aqueous. But the water is the solvent, that's a liquid. And no liquids allowed in the Kb formula. So I needed this H2O to get the right balanced equation, but in terms of your ice chart, we do not care about it. So just put an X right through it. Okay, they did say that we initially started off with a 0.050 molarity solution of nicotine. So that's going right over here, 0.050. They already gave me molarity, so that's the only unit that's allowed in here. 4 acids and bases. You could see gases, but generally it's going to be molarity. They did not state that I started with any of this, or the hydroxide ion concentration. So I'm going to say 0 and 0. Now C stands for change. Remember, if you start off with nothing, you could only go up from there. You can't get rid of nothing that you don't have, right? You can never have negative molarities. So we will be adding on the product side, which means that we will be taking away on the reactant side. But by how much? We don't know. So we label it as a variable. You could use A, B, C, D, E, F, G, X, Y, whatever, I don't care, right? I love how I went from A, B, C, D to X, Y, whatever. That's my alphabet. but we like to use x. So minus x, and plus x. The good thing about acids and bases is that it's generally going to be a 1-to-1 to 1-to-1 ratio. So x is around, all around. You don't have to worry about like minus 2x or plus 3x. It's just x's. E stands for equilibrium, and that's just your initial and your change combined. So 0.050 minus x is 0.050 minus x. 0 plus x is just x. 0 plus x is just x. And now we use this to put in for my Kb equation. So let's start it off. Kb1 equals, remember, any K value is always concentration of products divided by reactants. So it's going to be your 2 products divided by your 1 reactant. So if I just had to write it out, it would be C10H14N2H plus times OH minus divided by C10H14N2. Okay. Now, since this K value is so low, it's times 10 to the negative 7th. That means that at equilibrium, you're going to have mostly reactants. But here's the thing. If you start with all reactants and you're ending with mostly reactants, do you think this decrease is going to be big or very, very, very small? Yeah, it's going to be very small, right? And if it is very small, that means that the change is like negligible. This number is really not really going to change. So it still is here. But as far as the math purposes, we want to make our life easy. We can neglect this for the math. And we will only just place this value in for math. It still exists. We will still minus x at some point. But for the math purposes, we want to keep it as easy as possible. So we're just going to put in 0.050. Okay, so let's go for it. 7 times 10 to the negative 7th equals something divided by something else. It's your 2 products divided by your 1 reactant at equilibrium. So it's x times x, right? X times x divided by 0.050. Cross multiply. So it's the 7 times 10 to the negative 7th times this equals x squared. And maybe I'll just pull this up. So x squared equals 7 times 10 to the negative 7th times 0.05. 3.5 times 10 to the negative 8th. We want to get rid of the square, so we take the square root on both sides. That gets rid of the square. We just want x. Okay, take the square root. And I get 1 point, I guess it's 2 sig figs, so 1.9, I guess we'll say, 1.9 times 10 to the negative 4th. Okay, and that's molarity. So now we're starting because we now answered some of the questions. We want those species present at equilibrium. So we found out all of these 3 species. So let's just write it out. Maybe I'll start it over here and then I'll pick it up here. Okay, so we have a C10H14N2 H plus concentration, which was just X, right? Which was just X. So that was 1.9 times 10 to the negative 4th, and that's molarity. So let me pull this out a little bit more. Okay. We also have an OH minus concentration at equilibrium. That was just X. So that's 1.9 times 10 to the negative 4th molarity. Okay. And then for the actual nicotine, C10H14N2, that was 0.050 minus X. So remember when we were actually going to subtract the X? That's when we do it now. So it would be 0.050 minus the X value that we found, 1.9 times 10 to the negative 4th. So 0.05 minus 1.9 times 10 to the negative fourth. And, I mean, it's so close. It's literally the same number. But I guess I'll just write it all out. 0.04981. Roughly around there. Just to show you that, I mean, it did change a little bit, but not really. If you did round this, it would still be 0.05. Okay. So, now we did Kb1. But we need to now find out what's going on with the second proton. It will accept 2 protons. So now it's like a chain reaction. If this, or maybe I'll just write it out here, C10H14N2, we accepted 1 proton to get to C10H14N2H+. Now we're going to accept the second proton, right? And how many hydrogens now are here? 2 of them. So now it would be C10H14N2H2. Sorry that it's like running. Maybe what I can do is I could make this arrow a little bit smaller and bring this over here. There we go. Maybe I'll just write this over again. N2H2, and that's 2+. The first time was Kb1. That's exactly what we did. The second time is Kb2. And now here's the initial and final. Because when you're doing a K value, you can only gain 1 hydrogen at a time. So in this case now, we're going to start off with this first one and go to the second one. So all we have to do is just change this up a little bit. So pause the video if you need to. But I'm just going to get rid of the math here. So this is all going. We already got the X value. We wrote down all of our values. So pause the video if you need to write it down, but this is going. Bye-bye. And now I'm just going to get rid of these because these were the original starts. But I'm going to keep the ice table because we're basically just doing it again. And I guess I'll start from all the way to the beginning. But now, what you're starting with is you're not starting with the nicotine. You're starting with the actual product that you made. So this gets kicked out. Goodbye. And this comes over here. Look at that. That's good. We could pull this plus over here a little bit. And maybe get this. There we go. And just like we said now, we're going to add the second hydrogen. So this new product, still acting as a base, is C10H14N2H2. And now that's a 2+ charge. Because plus 1 is 2+. Okay. So now, here we go. Initial for this one was the final that we found. So in this case, what we found out here is the initial concentration now to start. So it's now going to be 1.9 times 10 to the negative fourth. So 1.9 times 10 to the negative fourth. Just like before, the water gets eliminated because it's a liquid. So bye-bye. And just like before, we didn't start now with any of this. So that's 0, but we did start with OH minus. Now we have OH minus. That's also 1.9 times 10 to the negative fourth. So I'm going to add that in. Okay. Same thing as last time. You can only go up from 0. So if you spot out a 0 initial, the products are going to be positive, because that's where the initial is, and the reactants are going to be minus. Just like before, it's minus X, and plus X, and your equilibrium is your initial plus your change. So it's 1.9 times 10 to the negative fourth minus X. 0 plus X is just X. 1.9 times 10 to the negative fourth plus X is 1.9 times 10 to the negative fourth plus X. Beautiful. Now we take the Kb2 information. So if I just swap this out for Kb2, this would be, for this following equation, is 1.4 times 10 to the negative 11th, even a smaller number. So the same reasoning behind the last one. Since our K value is so small, it's even smaller than the last one, the change is not going to be great. So I can get rid of this minus x. And to make things even easier, this plus x, that change is not going to be great because anytime that you minus x or you plus x, that's a change value. That's not going to be great. So we can get rid of this one as well. We can't get rid of this x value because if we did, we would have no x variable to solve for. So you just get rid of the minus x's and the plus x's. Okay, now let's do it. Kb2 equals, just to show it for you guys, we have the two products divided by the one reactant, just like we had before. But now it would be C10H14N2 H2, 2 plus, times OH minus, times C10H14N2 H. The Kb value was 1.4 times 10 to the negative 11th. Products divided by reactants at equilibrium. So we have x for this guy, 1.9 times 10 to the negative 4th, divided by 1.9 times 10 to the negative 4th. And look at that. This is the same number as the numerator and the denominator. So they actually go bye-bye. That makes it so much easier. X just equals 1.4 times 10 to the negative 11th. Okay. So let's now actually minus 1.4 times 10 to the negative 11th and plus 1.4 times 10 to the negative 11th. Let's see if it will even make a difference. I mean, they're such small numbers that it's probably not even going to matter. But we could add one more ion to the mix. We know that this is an x value. So the C10H14N2 H2 concentration is just the x value, which was 1.4 times 10 to the negative 11th. We're getting there, right? So we checked this one off. Let's just do this math. Let's just see if that number will change. 1.9 times 10 to the negative 4th minus 1.4 times 10 to the negative 11th. And it's, oh my gosh, it's 1.9 times 10 to the negative 4th. So we're going to keep it that way. So we're going to keep this, check. We had this from the beginning. We just found this one out. Let's do the OH minus. Let's see if that's going to change. 1.9 times 10 to the negative 4th plus 1.4 times 10 to the negative 11th. Yeah, no, not even going to budge. So these are all good. Maybe I'll just move this over a little bit. But now there's one thing. They said each species. And whenever you have an OH minus concentration, you secretly have a little bit of H plus. The H plus is not going to be in any of your balanced equations for bases, but it's still there. So we have to find that out. What's the formula? Well, Kw equals the concentration of these two times together, right? Concentration of, if we wanted to just put OH minus first, and then H plus, right? So pause the video if you need to. I just need a little bit more room. I'm just going to erase, I guess I'll just erase all of this. So pause the video if you need to, guys. It's just a lot of math here, so this is nuts. Okay, oh boy, what happened to that hydronium? There we go. All right, and if you want to solve for H plus, all you have to do is just divide by the OH on both sides, right? So I'm just going to do that real quick in the beginning. So it would just be Kw divided by the OH minus, and that equals H plus. So we have this formula, beautiful. The OH minus we found out to be 1.9 times 10 to the negative 4th. It is this value. That's the total. Technically it's this, but if you do the math just like we did before, it doesn't even move the number. And since they didn't tell us a temperature, but they did give us K values, we have to assume that we're at room temperature. So we have to use the Kw value that's at room temperature, and that's 1.0 times 10 to the negative 14th. So here we go. 1.0 times 10 to the negative 14th divided by that OH minus will give us the H plus, right? And this would be 1.9 times 10 to the negative 4th. So let's see. 1 times 10 to the negative 14th divided by 1.9 times 10 to the negative 4th. And the H plus concentration, which I will link up right here as our final concentration, is 5.26 times 10 to the negative 11th. And that kind of makes sense because if we are basic, we should have way more OH minus than our H plus. And that's it. Wow. I really hope this helped. If we actually just make this, if we want to just make this 2 sig figs, it would be 5.3. Does anybody really care? No, but just in case. Okay, there we go. Now we're done. Thank you so much. This has been a crazy ride. These are getting long, but I really hope that, step by step, I hope you guys are understanding it. Let me know in the comments what you guys think, and I will see you in later lessons. Okay, bye-bye.